Can public funding unlock real projects? Europe has approved a major new attempt to solve one of green hydrogen's biggest problems: cost. The Netherlands is preparing a €780 million renewable hydrogen support scheme designed to help producers compete with cheaper hydrogen made from fossil fuels. On paper, the Netherlands already has many of the ingredients required to become a major European hydrogen hub. It has extensive offshore wind resources in the North Sea, one of the world's most important ports, large refineries, chemical plants, industrial customers, and a developing national hydrogen network. However, infrastructure alone does not guarantee commercial success. The central question is whether this public funding can help real projects move through the difficult stages of development, from early announcements and engineering studies to final investment decisions, financial close, construction, and commercial operation. Because in green hydrogen, announcing billions in ambition is relatively easy. Building operating infrastructure that can produce competitively priced hydrogen is much harder. So, can €780 million of support finally unlock real Dutch hydrogen projects? Or will electricity costs, grid congestion, infrastructure delays, and weak industrial demand continue to hold the market back? Approval funds projects. It does not build them. Before examining the opportunity, we need to understand exactly what has been approved. This is not an announcement that a new hydrogen plant has already been constructed. It is not confirmation that hundreds of megawatts of electrolyzer capacity are currently operating. And it does not mean that renewable hydrogen is already flowing through Dutch pipelines to industrial customers. The €780 million package is a financial support framework intended to improve the economics of multiple renewable hydrogen projects. Projects may use the program to reduce part of the cost difference between green hydrogen and conventional hydrogen produced from natural gas. But approval of the support scheme is only the beginning. Individual projects still need to qualify for funding, complete engineering, secure sites, obtain permits, arrange renewable electricity, negotiate customer contracts, and raise the remaining capital required for construction. This distinction is extremely important. In the hydrogen sector, announced capacity is frequently presented as though it already exists. But there is a major difference between a project being announced, approved, awarded funding, financed, constructed, and placed into commercial operation. The Netherlands has approved a mechanism that may help projects advance. It has not automatically built those projects. Electricity, electrolyzers, grid connection, water treatment, compression, and storage. Green hydrogen is produced by splitting water into hydrogen and oxygen using renewable electricity. The underlying electrolysis process is well understood, but while the technology is technically proven, the commercial economics remain challenging. Electricity is usually the largest contributor to the cost of renewable hydrogen. A project may also require a large upfront investment in electrolyzer stacks, power conversion equipment, buildings, cooling systems, and balance of plant infrastructure. Before the electrolyzer can operate, the developer must also secure a grid connection or establish a direct renewable power supply. Water must be treated to a high level of purity. Once hydrogen is produced, it may need to be dried, purified, compressed, stored, or transported. Developers must also fund engineering studies, permitting, environmental reviews, insurance, project management, and financing costs. At the same time, many industrial customers are reluctant to pay a large premium for renewable hydrogen when conventional hydrogen remains cheaper. This creates a viability gap. The production costs may be higher than the price customers are willing or able to pay. The purpose of the Dutch support scheme is to reduce part of that gap and make early projects more investable. The Netherlands has several strategic advantages that make it a strong candidate for large-scale hydrogen development. First, it has direct access to the North Sea, where major offshore wind capacity is being developed. Second, it has large ports capable of handling energy imports, industrial materials, fuels, and chemical products. Third, it has substantial existing industrial demand. Dutch refineries, chemical plants, fertilizer facilities, logistics systems, and heavy industries already consume significant quantities of energy and hydrogen-related feedstocks. The country also has extensive natural gas infrastructure, some of which may potentially be adapted or repurposed for hydrogen transport. Its location provides access not only to Dutch customers, but also to neighboring markets in Germany and Belgium. This matters because a large hydrogen project needs more than production facility. It needs renewable electricity, industrial customers, pipelines, storage, import infrastructure, and access to regional markets. The Netherlands brings many of these elements together within a relatively compact geography. That creates the possibility of developing an integrated hydrogen ecosystem rather than a collection of isolated projects. The opportunity is significant, but every part of the system must develop at the right time. The connection is physical and contractual. Offshore wind could provide much of the renewable electricity required to produce green hydrogen in the Netherlands. The physical pathway appears straightforward. Wind turbines generate electricity in the North Sea. That electricity travels through offshore cables to onshore substations. From there, power can be delivered to an electrolyzer facility where water is separated into hydrogen and oxygen. However, connecting wind power to hydrogen production involves more than constructing cables and installing equipment. The relationship is also contractual. The hydrogen developer must secure access to renewable electricity under terms that support long-term project financing. This may involve a power purchase agreement, a direct connection to renewable generation, or another compliant electricity supply structure. The developer must also understand how often the electrolyzer will operate. An electrolyzer that runs for many hours each year can spread its capital costs across a larger quantity of hydrogen. But a system that operates only when excess wind power is available may have a lower utilization rate. That can increase the cost of every kilogram produced. So the key issue is not simply whether offshore wind exists. It is whether the project can obtain affordable, reliable, and compliant renewable electricity for enough operating hours. Power conversion, water purification, electrolyzer stacks, gas separation, and compression. The electrolyzer is the central component of a green hydrogen plant, but it is only one part of a complete system. Electricity arriving from a grid or a renewable power source must first be conditioned. Power conversion equipment adjusts the incoming electricity so it can be used by the electrolyzer stacks. At the same time, the facility needs a reliable water supply. That water must be treated and purified because electrolyzer systems generally require high-quality feed water. Inside the electrolyzer stacks, electrical energy separates water into hydrogen and oxygen. The resulting gases must then be managed safely. Hydrogen may require additional separation, drying, and purification before it meets the specifications required by the customer. It may then be compressed for pipeline delivery, storage, or transport. Depending on the project design, the facility may also include cooling systems, electrical substations, water tanks, control systems, safety equipment, and temporary hydrogen storage. Each of these components affects efficiency and reliability. A failure in the power electronics, cooling system, water treatment unit, or compressor can reduce production even when the electrolyzer stacks themselves are functioning correctly. That is why developers must evaluate the complete plant, not only the electrolyzer. Production, imports, and distribution in one port. Rotterdam could become one of the most important hydrogen gateways in Europe. The port already handles enormous volumes of oil, natural gas, chemicals, fuels, and industrial materials. It serves refineries, chemical facilities, logistics companies, and manufacturing customers throughout the Netherlands and beyond. In the future, Rotterdam could support several hydrogen pathways. Renewable hydrogen could be produced locally using electricity from offshore wind. Hydrogen could also be imported from regions with stronger renewable resources and lower production costs. Because transporting pure hydrogen over long distances can be difficult, some imports may arrive in the form of hydrogen carriers such as ammonia, methanol, or other chemical derivatives. These carriers may be used directly in industry or converted back into hydrogen. From Rotterdam, hydrogen could move through pipelines toward inland industrial clusters and neighboring countries. This means the port's role could extend far beyond one local production plant. It could become a platform for domestic production, international imports, storage, conversion, and regional distribution. But turning Rotterdam into a true hydrogen gateway will require coordination between ports, project developers, pipeline operators, industrial customers, and government agencies. Refining, chemicals, fertilizer, steel, e-fuels, and heavy transport. The long-term success of the Dutch hydrogen market will ultimately depend on demand. Hydrogen plants cannot survive simply because governments want them to exist. They need customers who can purchase predictable volumes under commercially credible agreements. Potential users include refineries that already consume hydrogen for fuel processing. Chemical facilities may use hydrogen as a feedstock. Fertilizer producers may require hydrogen for ammonia production. Steel manufacturers may use hydrogen to reduce emissions from iron and steel production. Synthetic fuel projects may combine renewable hydrogen with captured carbon dioxide to produce e-methanol, e-kerosene, or other fuels. Some heavy transport applications may also use hydrogen directly or through hydrogen-derived fuels. However, these customers face their own commercial pressures. They need hydrogen at a price that allows them to remain competitive. They also need confidence that supply will be reliable and that the hydrogen will satisfy European renewable fuel certification rules. Without bankable customers, a technically sound project may still fail to secure financing. That is why industrial demand, not electrolyzer manufacturing capacity, may become the decisive factor. Support should launch a market, not sustain one. The purpose of public support is to reduce part of the financial disadvantage faced by renewable hydrogen. The exact mechanism may vary. Funding could help cover part of the initial capital investment required to build production facility. It could help compensate producers for the difference between the cost of renewable hydrogen and the market price customers can pay. It could also provide a production-based premium for each unit of qualifying hydrogen. In each case, the objective is similar: reduce the viability gap enough for developers, customers, and lenders to proceed. However, public support must be designed carefully. A subsidy should ideally help launch a new market, reduce early project risks, and support learning. It should not create a system in which projects can survive only through permanent government payments. Over time, developers will need to reduce costs through cheaper renewable electricity, more efficient equipment, improved utilization, larger projects, and better infrastructure. Industrial demand must also mature. The €780 million scheme may help the Netherlands start this transition. But the real measure of success will be whether supported projects can eventually operate on a stronger commercial foundation. Grant, sponsor equity, concessional debt, commercial debt, guarantee, and offtake contract. Government support is important, but it is only one layer of a complete project financing structure. A large green hydrogen project may require several sources of capital. A grant can reduce the amount the developer must finance. The project sponsors may contribute equity and accept the earliest or highest level of risk. Concessional lenders may provide financing on more favorable terms than a traditional commercial bank. Commercial debt may fund part of construction costs once major risks have been addressed. Guarantees may protect lenders from specific political, market, or performance risks. And most importantly, long-term offtake agreements provide evidence that the project will have customers and future revenue. Lenders will examine every major assumption. They will assess electricity costs, technology performance, construction schedules, permitting status, infrastructure access, and customer creditworthiness. They will also consider whether the project complies with renewable hydrogen regulations. A funding award may improve the economics, but it will not automatically satisfy all these requirements. A bankable project requires a complete financing stack supported by credible contracts, engineering, and risk allocation. Producers need somewhere for the hydrogen to go. Hydrogen plants cannot succeed in isolation. Once hydrogen is produced, it must reach a customer. That may require a direct pipeline between the production facility and a nearby industrial plant. For larger regional markets, it may require access to a national hydrogen network. The Netherlands is developing infrastructure intended to connect ports, industrial clusters, production sites, storage facilities, and neighboring countries. If that network becomes available on schedule, producers may be able to reach a much larger group of customers. This can improve project economics and reduce dependence on one buyer. However, if the pipeline is delayed, the production facility may be completed without an efficient delivery route. The developer may then need to depend on a limited local customer, temporary storage, or truck-based transportation. Those alternatives can be expensive and may only be practical for small volumes. Timing is therefore essential. The electrolyzer, renewable power supply, storage system, customer facility, and hydrogen pipeline must all become available within a coordinated schedule. If one major component falls behind, the entire project can suffer. Variable wind, steady industrial offtake, renewable electricity production, and industrial hydrogen demand do not always follow the same pattern. Offshore wind output changes depending on weather conditions. Industrial customers, however, may require stable hydrogen supply throughout the day. A refinery or chemical plant cannot simply stop operating every time wind generation falls. Storage can help balance these differences. When renewable electricity is abundant, the electrolyzer may produce more hydrogen than the customer immediately needs. That excess hydrogen can be stored and delivered later. Above-ground tanks may provide short-duration or operational storage. For much larger quantities, underground salt caverns may offer a potential solution. However, storage introduces additional complexity. Hydrogen must be compressed before it enters many storage systems. Storage facilities require permits, monitoring, safety systems, and specialized infrastructure. Energy is also consumed when hydrogen is compressed, stored, and withdrawn. Storage can improve system reliability, but it increases project cost. Developers must determine how much storage is necessary and whether the benefit justifies the added investment. Funded capacity still waits for a connection. One of the largest risks facing Dutch hydrogen projects is the electricity grid. Several areas of the Netherlands are already experiencing significant grid congestion. Renewable projects, industrial facilities, and new electricity consumers are competing for limited network capacity. A hydrogen developer may secure land, complete engineering, and even order an electrolyzer. But without an electrical connection, the facility cannot operate at its intended scale. Connection delays may last several years in constrained areas. That creates a difficult problem. Project financing depends on a clear construction and commissioning schedule. Customers need confidence about when hydrogen deliveries will begin. Equipment suppliers need confirmed delivery dates, and government support may be tied to specific development milestones. A delayed grid connection can disrupt all of these arrangements. Some projects may seek direct connections to renewable generation. Others may use behind-the-meter systems, flexible operation, or hybrid power arrangements. But these solutions involve additional engineering and regulatory considerations. A project may receive funding and still fail to advance if it cannot secure sufficient electrical capacity. Additional power, geographic matching, time matching, certification, emissions. Producing hydrogen with electricity does not automatically make it renewable. European rules require developers to demonstrate that the electricity used by an electrolyzer meets specific renewable energy conditions. These requirements are intended to ensure that hydrogen production does not simply increase demand for fossil-based power. Developers may need to demonstrate that renewable electricity generation is additional to what already exists. The renewable power source may need to meet geographic requirements relative to the electrolyzer. Electricity generation and hydrogen production may also need to be matched within defined time periods. Projects must maintain certification records and calculate the emissions associated with a full production pathway. These rules protect the environmental credibility of renewable hydrogen. However, they can also make project development more complex. Strict time matching may reduce the number of hours during which the electrolyzer can operate. That may lower utilization and increase the cost per kilogram of hydrogen. Developers must therefore balance regulatory compliance, operating flexibility, and project economics. The cleanest theoretical design may not always be the most financeable practical design. Price, volume, delivery, certification, and duration. No green hydrogen project can reach financial close without credible customers. An offtake agreement defines a commercial relationship between the hydrogen producer and the buyer. It establishes how much hydrogen the customer will purchase. It defines the price or pricing formula. It identifies when deliveries will begin, how long the agreement will remain in place, and what happens if either party fails to perform. The contract may also include requirements related to hydrogen purity, renewable certification, delivery pressure, and emissions performance. These details are essential because lenders depend on future project revenue to repay debt. However, industrial customers may hesitate to sign long-term agreements. Renewable hydrogen remains expensive. Future regulation may be uncertain. Technology costs may decline. And some buyers may expect government policies to reduce their risk before they commit. Developers therefore face a difficult negotiation. They need strong long-term agreements to secure financing, but customers may prefer shorter or more flexible contracts. Until this commercial gap is resolved, many projects may remain in development. Efficiency, degradation, warranty, maintenance, availability, and spare parts. Electrolyzer manufacturers are expanding production, introducing new systems, and competing for large project orders. For developers, the lowest purchase price may appear attractive, but equipment cost is only one part of the project decision. Developers must evaluate how efficiently the system converts electricity into hydrogen. They must understand how quickly the stacks degrade and when major replacements will be required. Warranty terms must be carefully reviewed. The developer must determine which performance guarantees are provided and what happens when the system fails to meet them. Maintenance requirements, system availability, and access to spare parts also affect long-term production. A low-cost system that suffers frequent outages may produce more expensive hydrogen over its lifetime than a higher price but more reliable alternative. The financial strength of the equipment manufacturer also matters. Green hydrogen projects may operate for decades. The developer needs confidence that the supplier will remain capable of honoring warranties, providing service, and replacing critical components. Technology selection is therefore not simply a procurement exercise. It is a long-term project risk decision. Announcement, approval, award, FID, financial close, construction and operation. Hydrogen project success must be measured by more than the value of announcements. The development process contains several distinct milestones. An announcement communicates an intention. Government approval may establish a funding program. An award may provide support to a specific project. A final investment decision means the sponsors have formally committed to proceed. Financial close means the required financing agreements have been completed and the project can access construction capital. Construction then begins. After installation, testing, and commissioning, the facility may finally enter commercial operation. Each stage eliminates some uncertainty, but each stage also introduces new challenges. Many projects attract attention at the announcement stage. Far fewer complete financing, and fewer still reach full commercial production. The real test for the Dutch scheme will not be the number of press releases it generates. It will be the amount of supported capacity that reaches final investment decision, completes construction, and begins applying certified renewable hydrogen to real customers. That is the difference between promise and production. Europe is watching the Dutch experiment. The Dutch program could become an important test case for the wider European hydrogen market. Many countries face the same basic challenge. Renewable hydrogen is needed for industrial decarbonization, but early projects remain expensive. Governments must decide how much support to provide, which project to select, and how to avoid funding facilities that never become commercially viable. If the Dutch approach succeeds, it could demonstrate how public support, industrial demand, renewable power, and infrastructure can be coordinated. It could provide a model for supporting projects without creating permanent subsidy dependence. It could also accelerate cross-border hydrogen trade between the Netherlands, Germany, Belgium, and other European markets. But if projects remain delayed by grid congestion, weak offtake, regulation, or infrastructure problems, the program could become a warning. Europe would learn that funding production alone is insufficient. The complete system must be developed together. The Netherlands, therefore, represents more than one national funding program. It is an experiment in whether Europe can convert hydrogen policy into operating industrial infrastructure. Site, power, water, permits, financing, offtake, and infrastructure. For project developers, the lesson is clear. A green hydrogen project is far more than an electrolyzer. It begins with a suitable site, The site must have access to renewable electricity, water, transportation, and industrial infrastructure. The project needs engineering studies, environmental reviews, permits, and community engagement. Developers must select appropriate equipment and negotiate contracts with technology suppliers, engineering firms, and construction companies. They need a financing structure combining grants, equity, debt guarantees, and other forms of capital. They must secure customers through credible offtake agreements. And they must ensure that pipelines, storage systems, or other transportation methods are available when production begins. Every component is connected. A weakness in one area can affect the entire project. H2 Hub helps clean energy project developers research hydrogen projects, technologies, equipment, financing pathways, and project development requirements. Explore the platform at h2hub.renenergy.com and use it to better understand the systems required to move a clean energy project from concept toward bankable infrastructure. Funding can open the door. Execution determines success. The €780 million Dutch hydrogen scheme could help unlock a new generation of industrial renewable hydrogen projects. It may reduce the cost gap, improve project economics, and encourage developers to move forward. But funding alone cannot guarantee success. Projects still need affordable renewable electricity. They need timely grid connections. They need reliable electrolyzer systems and strong equipment suppliers. They need hydrogen pipelines, storage, and industrial customers. They must comply with European renewable hydrogen rules. And they must raise enough capital to complete construction. The Netherlands has many of the strategic advantages required to become a major hydrogen hub. It has offshore wind major ports, industrial demand, international connections, and extensive energy infrastructure. But the outcome will depend on execution. The real test begins when projects move beyond announcements, reach final investment decisions, complete financing, enter construction, and begin producing hydrogen. Funding can open the door. Engineering, infrastructure, financing, and customer demand will determine whether projects walk through it. Subscribe to Renee Energy for more engineering and project development analysis covering green hydrogen, clean energy infrastructure, and the systems behind the global energy transition.